Okay, so let's go ahead and start chapter 10. We're going to go ahead and start with the means being independent with two samples. That way we don't have to worry too much. We'll deal with the dependent sampling in just a little bit. So here in this chapter, when you're testing about two samples, they get kind of intense, the formulas. So I put a little note in here just stating that we're going to be using statistical technology with highlighted. Okay. As we can see down here, with two population means that we still have the criteria of the sample should be independent, still have to meet that greater than or equal to 30. Now, if they aren't greater than or equal to 30, remember that we can go ahead and just, if it's raw data, we can go up, do a box plot and a normal probability plot like we did in the previous section in chapter 9, 9.5. So, and then we still need to ensure that the sample size is no more than 5% of the population. However, when we get into the testing, you can see that the t-value and the degrees of freedom, they become a little much for us, right? So that's why we're just going to use our calculator and technology for it. So how are we going to go ahead and do the test? Well, we're going to determine the null and alternative as we usually do. They'll say the first sample greater than decrease. We use the same thing. If it's less than, greater than, or equal to, it's still left tail, right tail, two-tailed, respectively. And then we'll go ahead and draw the figure and determine level of significance. And we just put it in the calculator. And we can use now the two sampler and then run all the stats there. So, and then step 5 is always making that conclusion. So if we go ahead, scroll down a little bit, we're going to see the calculator commands here for two sample t-tests. So our calculator and hit stat and go to tests and go to 2samp t-test. Now number 9 is 2samp z-int. Now you can see number 3 is 2samp z-test, and then number 4 is 2samp t-test. Chapter 9, testing about one sample, and two samples would be number 4, 2samp t-test. So if I go ahead and hit number 4, you can see that they have data that you can put in a list. And also, if you go to stats, hit enter, it brings up a new menu with given statistics. So we're going to have an example of both. Okay, so let's go ahead and do the example. Company A samples 15 workers and their average time with the company is 5 years with standard deviation of 1.2. Company B samples 20 workers and their average time with the company is 4 and 5% significance level. So I think the biggest red flag here is we assume that the populations are normal because at that point when we have to do our preliminary is the sample sizes, which has 15 workers, and we have to make sure that is no more than 5% of all workers at the company. So for company B, we need to make sure that the sample size N sub B which is 20 workers, is no more than 5% of all workers at company B. Okay, and then what's nice about this one, that tells us that our samples are independent. However, it is given to us that the populations are normally distributed. I think now we can go ahead and conduct the hypothesis test among two samples. And so now we kind of talk about, well, because they give us a mean and because they give us a standard deviation, we know this is a test among means. And so we'll compare two sample means and then take it to comparing to population means. Okay, so step one is always setting up your hypothesis. So let's go ahead and do that. We're comparing two means, mu sub A for company A and mu sub B for company B. And so now we have to look at the alternative hypothesis is usually the claim, and we determine if company A retains its workers longer than company B, then what does that mean, right? If it's longer, that means a person is working at company A longer and their number of years is larger than the number of years worked in company B. So this means that it would be the mean of company A is greater than the average number of years worked at company B. So step two is now to draw the figure. So let's go ahead and draw that normal curve where we have the mean, the population parameter in the middle. We know that by the alternative hypothesis that this is a right tail test. And so we'll do a little right tail shading. We're testing at a 5% significance level. So that means our alpha is equal to 0.05. And so we'll go ahead and just label that on the graph. The fourth step is always the finding the p-value, and that's where we need the calculator, right? So let's go ahead and write down our statistics for each company. So company A had 15. The sample mean was 5, and the standard deviation was 1.2 years. Company B was a sample size of 20 with an average of 4.5 years with a standard deviation of 0.8 years. So if we just go ahead and go into our calculator and enter this in, as we saw before in a 2-SAMP t-test, so we'll go to stat, go to tests, and then go down to number 4, the 2-SAMP t-test. And we have statistics given to us, so we're going to go ahead and enter those in. So make sure that when you enter in statistics that you are using X1 that goes with the first parameter listed, which was company A, and X2 be corresponding to the second parameter listed, which is company B. So if you just keep those straight, your hypothesis testing will be accurate. All right, so just entering in, so X1 would be company A, so the average is 5, standard deviation was 1.2, and the sample size was 15. Company B, the average was 4.5 years, with a standard deviation of 0.8 and a sample size of 20. Go ahead and select the correct hypothesis where we thought the average number of years was greater than in company A than B. Make sure pool is marked no. My favorite color is blue, and you can go ahead and calculate. Let me go ahead and drag this over to our notes so that way we can refer to how we entered our data in the calculator. Okay, so now let's go ahead and calculate this. Hit calculate, enter. And we can see like a series of, information that they give us. They give us the roundup of what we entered. Notice the degrees of freedom are like weird. They're not just like the sample size -1. And that's because of those formulas in the very beginning that we discussed that were kind of advanced and likely to make error if we did them by hand. Even our statistic. If you can see that it calculates it for us. That's why technology is such a nice tool for us to use because it calculates these simple things or more complex things in a simpler way for us. So let me go ahead and drag that over. All right. Okay, so let's go ahead and write down we use the p-value approach, and we see that the p-value is one second. So the p-value is 0.0878. And our alpha that was given to us is 0.05. And if we compare these two numbers, we can easily see that this p-value is much larger than our alpha. And so because the alpha is larger, the p-value is larger than the alpha, that means the area which is in red, is bigger, right? That means the probability that I take another 2 samples from each of these companies and get the same results is highly likely. And that means that there's just not enough evidence to support change, right? Like it seems like there's enough evidence to just keep status quo and there should be no change. And therefore, because this probability is larger than our alpha, we have to go ahead and reject the null. Or do not reject the null. Sorry, do not reject the null. So if we do not reject the null, this means that we accept the null and we have to reject the alternative. And because the alternative was our claim, that means, do we support our claim? Well, no, right? And so there is not enough evidence to support the claim that companies A, workers work longer on average than company B, right? So let's go ahead and write this out in step 5. So there is not enough evidence to support the claim that company A's retains its workers longer than company B.